Thank you, Ian, for launching us this morning. I'm delighted to introduce my two colleagues, and I'll start by saying that we share some history. So Larry, Chris, and I all were involved in straw bale construction starting in the 90s. And we didn't meet, I didn't meet Chris until much later. Larry and I met pretty much in the 90s. So we've been playing in this space for a long time. And both of us, I guess all three of us really have been very concerned about embodied carbon that entire time. So in fact, I did my master's thesis with a focus on embodied carbon in 1995. So it's been a long road, and I'm absolutely tickled to be able to have persuaded these two leading lights in this field to put this class together for you all, as they continue to innovate and educate and inspire many, many people within our industry. As Ian said, Chris has recorded his presentation because he's off somewhere in the remote areas of Ontario where he lives, Ontario, Canada, that is. However, he will be able to join us for Q&A at the end. So if you have questions that come up during Chris's portion, jot them down and you'll be able to quiz him when the time comes. So about Chris, he has been in the building field for a quarter century, built his first permitted straw bale house in Ontario in 1996. And since then, he has designed and built many, many other buildings and really been focusing very much on the embodied carbon issue most recently. He did a master's at Trent University a few years ago where he studied the carbon storage potential of the built environment, published a thesis on this subject, and has been really completely enmeshed in helping educate the rest of the folks in our field about this ever since. He has also authored 7 other books on sustainable building and has another book that is somewhere in the publication process at the moment, co-edited with Bruce King, called Building Beyond Zero, New Ideas for Carbon Smart Architecture, in which I believe Larry and I both have chapters. So there we go. We are conspiring once again. So on to Larry. As I mentioned, Larry and I've known each other for a very long time and had many opportunities to collaborate and conspire in this field, which has been great fun. He is one of the founders and principals of Siegel Strain architects in Berkeley, California. Sorry, Emeryville, on the edge of Berkeley. And Siegel Strain has won many, many top design awards from the AIA and other organizations for their groundbreaking work in sustainable design, along with his partners who are quite numerous at this point. And actually, Larry and his partner Henry, who started the firm, are now kind of taking the back seat and putting even more time and energy into this research area. So that's why Larry may be less involved with the firm at this point, but he is by no means leaving the industry. Leading, he is leaving, he is not. So with that, I will turn it over to Larry. Take it away. Thanks so much for being here.
Okay, I think that's it. Great, thank you so much. We're happy to be here. I'm happy to be here. Chris is virtually happy to be here. We're going to talk about embodied carbon and why it's important and how to minimize it. So let's do, I'm going to get this at some point. So this is kind of what the day is going to look like, what it is, why it's important, embodied emissions from buildings and sort of the time value of carbon emissions, reducing embodied carbon using standard materials and methods, which is a case study that I'll be sharing. And then Chris has got a whole thing on carbon storing and carbon sequestering materials that will be pre-recorded, which will show that. And then I'm going to close by talking about the importance of existing buildings in this whole discussion about embodied carbon and a little bit on tools that are available. So starting with definitions, First of all, when we talk about carbon in this slideshow, we're talking about all greenhouse gases. We probably already know that, but it's all the methane, carbon, CO2, everything. It's all just a shorthand for talking about that. Operating emissions are all the greenhouse gas emissions from operating a building, and it includes direct emissions from on-site fossil fuel combustion at the building and indirect emissions from the electricity used to power the buildings. And these emissions are ongoing and cumulative over time. Embodied emissions are the carbon footprint of a material, the greenhouse gas from extracting, processing, and transporting the emissions. And it typically represents a huge hit of carbon emissions at the beginning of a building's life, but it also includes emissions from maintenance and repairs that happen over time as well. Embodied carbon doesn't have to be emissions, it could also be stored or sequestered. Avoided carbon, which we'll talk about too, is about the savings from a particular choice. For instance, renovating and upgrading a building compared to tearing it down and rebuilding it, or building with carbon sequestering materials compared to building with materials that generate carbon emissions. You've probably seen this chart before, many of you have. Buildings make up about 40% of global emissions. 28% is from operating all the buildings we already have, and 11% is the embodied emissions from buildings. And the point I like to make with this is that operations is mostly existing, embodied emissions are mostly new, although it does include renovations of existing buildings, but most of the emissions are coming from building new buildings. The majority of embodied emissions happen when the building is built. What this means is for the buildings we build between now and 2030, if we continue to build the way we currently build, about 80% of their carbon footprint will be embodied. So for new buildings, over the next critical 10 years, reducing embodied emissions is key. To tackle operating emissions, we need to make new buildings net zero, but even more importantly, we need to reduce the operating emissions from existing buildings, and we'll get to that later. The majority of embodied emissions typically are from the materials we build with. They make up 70 to 80%. The rest are emissions directly associated with construction, the site work and utilities required for the project. Many embodied carbon studies leave out these other emissions, and many aren't even counting all the materials. Some only include structural materials. These percentages will vary by project. Sometimes site work or transport can be significant, but the bottom line is most embodied emissions are currently from the materials we build with. Embodied emissions vary by construction type. This is what it looks like for how we currently build. Average emissions for new buildings range from about 500 kilograms of emissions per cubic meter for a large concrete steel building, down to about 250 kilograms for light wood frame buildings, like typical homes in the US. Renovations, when they can save the high carbon parts of the building, the structure and the foundation, have a much smaller footprint compared to new construction. And it's possible to reduce all of these more by using low carbon materials. In a few minutes, Chris is going to talk about carbon storing and carbon sequestering materials and how to make this graph drop below zero. But I want to start by talking about standard materials and practices.
Larry, before you go on, could you go back to that last slide? So when you say, for example, 500 kilograms per square meter, do you mean per square meter of floor area?
Yeah, it's typically measured in floor area. Yeah.
Okay, great. Thank you.
Sure.
Yeah,
and this is based on
what's that? I heard you say cubic meter, but the graph was in square meters.
It's in square meters. Yeah, it's in square meters. I misspoke. All right. So our firm knew about the importance of embodied carbon since, as Anne mentioned, the early 90s. But at first we just focused on reducing the carbon footprint of concrete because we knew how important it was. We didn't know much about the embodied emissions from all the rest of the materials. The first project we tried to do this on was the Portola Valley Town Center, a LEED Platinum, really efficient project built with a conscious effort to use low impact, low carbon materials. This is designed with Goring and Strada architects and an incredible team of consultants. The town had occupied an old school on an 11-acre site, which the district had abandoned 20 years earlier because it sat directly on top of the San Andreas Fall, which are those pink lines. These are traces of the San Andreas in Portola Valley. The existing buildings on the left were deconstructed and the materials were reused in a new town center just outside the fault zone. We were also able to reduce the building footprint in paved areas and increase the landscape and playing fields. We had a very involved community and a lot of input from the community on the project throughout the project, which was really helpful. Restoration was an important part of the project. We introduced a lot of native planting and habitat. This is a portion of the creek that we uncovered, and it forms the fourth side of the town green. The community hall is in the background. So after it's completed, we decided to try and measure all of the carbon emissions from building the project, the embodied CO2. This is before there were tools like Tally available, so the first thing you had to do to calculate the carbon footprint was figure out how much everything weighed. And you can see that the concrete foundations and slabs accounted for most of the weight. About 80% of the weight of these buildings was concrete. This is even though these were wood frame buildings, clad in wood, with wood paneling, wood ceilings, and some wood flooring. Wood only accounted for 12% of the total weight of the project. Next, we calculated the carbon footprint of all the materials using a carbon database that gave us kilograms of emissions per kilogram of material. Again, concrete accounted for the largest amount, but only 40% of the total emissions were concrete. Wood was about 12%, steel a little over 13%, even though by weight we used half as much steel as we did wood. The new framing lumber was all FSC certified, and most of the rest of it was reclaimed. We didn't count sequestration for the new lumber, which would have lowered our wood number significantly. So then we modeled a base case project using standard material choices, which are the orange bars on this chart, and compared it to the materials we actually used, which are the blue bars. Concrete not only accounted, on the far left there, concrete not only accounted for the largest portion of emissions, it was also where we realized the largest savings, about an 80-ton reduction from using a high slag, high fly ash concrete mix. The other interesting thing we learned was that we saved about 40 tons by using the salvaged wood. It shows up here as a negative number on this chart because A, the salvaged wood is not going to landfill and decomposing and turning into methane, and B, because the trees we didn't have to cut down are still growing, sequestering carbon. The overall reduction was a little over 30%. And this was really mostly from those two sources, from concrete and reclaimed wood. There are other ones where we saved a little bit here and there, but that was, you can see the down at the bottom, the reductions in each category, and the largest one is in structure. But finishes, which includes the wood, was also pretty large. This is the multi-purpose room in the community hall and the reading room in the library. Almost all the wood was salvaged from the old school buildings, remilled and used on the ceilings and walls. The floor in the multi-purpose room is eucalyptus from trees that were cleared for fire safety reasons and milled and dried within a few miles of the site. Everybody got on board with the salvaged wood. The town, because it recalled the old school buildings, which they had loved, and the contractor also really got into it. When he realized we were running out of salvaged wood from the old school, he took the wood crates that the metal roofing came in and remilled it and used it for window trim without even asking us. He just went ahead and did it, which we thought was great. All of the exterior siding is salvaged redwood from Northern California, a nod to the many tall redwoods growing on the site. The sunshades are salvaged yellow cedar, chosen because it weathers to a silvery gray, which better bounces light into the buildings. The beams supporting the sunshades were also salvaged from the old school buildings. So, how do the embodied emissions compare with the operating emissions for this project? As usual, for operating, we started with a passive approach. Maximize natural ventilation and daylighting, minimize heat gain with shading, use thermal mass for nighttime cooling, and we modeled this all with our engineers to optimize our choices. After we had done all that, we were in the position to use small, very efficient mechanical systems, which saved both first cost and operating costs. The buildings use about half as much energy as a building designed to California Title 24, and most of that was supplied by on-site PVs. Embodied carbon, embodied CO2, is usually counted as so many years worth of operating CO2. And over the projected 100-year lifespan of these buildings, even accounting for increases due to repairs and maintenance, the embodied emissions for the as-built project were about 13% of the projected operating emissions, which wasn't very significant. But here's the thing. We don't actually have 100 years. We have about 20 years to get to zero. When you focus on the next 20 years, the embodied emissions are about half the total. But even that's not the whole story. Embodied emissions and operating emissions don't happen at the same time. Embodied emissions happen at the beginning of a building's life mostly, before operating emissions even begin. So it's not just how much carbon you save, it's when you save it that matters, maybe even more. Here's why. We call this the time value of carbon. We borrowed this graph from a book called Heat by George Monbiot, a British writer and climate activist. This is a page from an article I wrote for Building Green many years ago, at this point, 15 years ago. The lines represent different rates of greenhouse gas reductions. The middle line is a steady 10% reduction per year. The green line up at the top starts slow and then increases the rate of reduction over time. The red line starts fast and then tapers off. The area below each line is the total carbon emitted over time under each scenario. The red line wins. Early savings matter. Saving embodied carbon front loads building savings. There are also ways to reduce embodied carbon even more, which Chris is going to talk about. And now, I hope, through the wonders of technology, we're going to hear from a pre-recorded Chris to tell us about more radical ways of approaching embodied carbon emissions.
Hey everyone, thanks for inviting me to present with you today. I'm really sorry that I'm not presenting live. The opportunity to share a stage with Larry and Anne is always a pleasure, and I'm really hoping that I will be jumping in on the Q&A session. So if you have any questions about what I'm presenting, please hold on to those, and we'll take care of that at the end of the session. Briefly, my name is Chris Magwood. I work with Builders for Climate Action in Ontario, Canada, and I'm going to be presenting today on turning buildings into carbon sinks, looking at the accounting for and the types of materials that can do that, and also a couple of case study buildings that I've been involved with in my practice up here in Canada. So I just want to start by kind of grounding my devotion to this work to the sort of upcoming generation. I have a daughter who's in her late 20s now, and she was part of kicking me into really paying attention to the carbon footprint of my buildings. She has known, growing up that I do this green building thing. She grew up in a straw bale house, so she knows, a little bit about this. But, one day she sort of asked me, she was about 16, like, Dad, is this stuff you're doing, like, is it going to save the climate? And that was really, it was a jarring moment for me because, I had been doing green building for 20 years at that point, and, felt really well grounded in knowing that my buildings were energy efficient and that they were healthy and that they were using local resources. And, we'd really been paying attention to all kinds of factors, but climate change just hadn't been central to that. I guess I'd always assumed, oh, I probably am. But that question, and then the sort of less than questions, the sort of demands from the younger generation really spurred me to, in my own practice, try to figure this out. And that has kind of led to trying to help others do the same. So I'm going to start just by talking about how current life cycle assessment practice works for biogenic carbon. Works might be in air quotes because I don't think it really does work right now. I think it's a real flaw in LCA, how biogenic carbon is handled. It makes sense. It was not, when people started doing life cycle assessment for buildings, carbon storage was not really on the agenda, and in a lot of ways still isn't, because the only biogenic material people really consider to date is wood, and we'll get into sort of wood and timber products and how this works for them. But in current LCA, there's actually, you're allowed to account for biogenic carbon in 3 different ways. And that in itself is confusing because, anybody doing an LCA can choose any of those 3 ways, which automatically means their results aren't really comparable to somebody who's chosen one of the other 2 ways. And the first way is kind of, it basically just says ignore biogenic carbon. You sort of make this assumption that a bunch of carbon comes out of the atmosphere and ends up in this biogenic material, before it's turned into a product. And you just assume that at the end of its life, all of that carbon is going to come out into the atmosphere. So you just call it 0. You basically just ignore it completely. And even though that seems really strange, it's considered a valid means of addressing biogenic carbon in life cycle assessment. And shockingly to me, even manufacturers of products with significant amounts of biogenic carbon in them produce LCAs and environmental product declarations based on those LCAs in this fashion. So you have things like the cellulose industry, put out an environmental product declaration which completely ignores the fact that their material is a massive source of biogenic carbon storage. So this is the 0-0 method, and it's still quite common. I hope that we'll see this fade as everybody realizes the value of biogenic carbon, but currently this is still considered a valid way of addressing this. The -1+1 method is somewhat similar in that it counts, you sort of, in your assessment, you count the carbon that was pulled out of the atmosphere and is stored in the material at the front. So in the A1 sort of harvesting section of an LCA, you say, if there's 20 kilograms of carbon stored in this material that came out of the atmosphere, you say there's a -20, like 20 came out of the atmosphere. And then at the end of the life cycle, you say, and that 20 came back out here. Or you can say, well, not all of that 20 came out at the end. We're gonna, say that, X amount of the material goes to landfill, and therefore this much carbon comes out, or this much of it gets incinerated, and so this much carbon comes out. But essentially, you're kind of using the minus and the plus to come up with a figure for the end of life, and it's usually ends up being a positive number. So showing that the material still has sometimes a significant carbon footprint, even though it has this large amount of carbon stored in it. Oops, sorry. So this seems like it should be a good way to do this, but it highlights a really critical issue with LCA practice as it's done right now, which is that it ignores the importance of time in thinking about emissions and carbon storage. So we tend to fixate on that, the final number for a material when we're looking at LCA. We add up all the minuses and we add up all the positives, and we get to this number, at the end of life that's the total of all of those things. And that single factor tends to be what we use for making comparisons between materials. So, if we kind of use the -1+1, but only pay attention to the end result, we miss a whole lot. And what we miss is that, here's that sort of map of a biogenic material. So there's a big drawdown in the A stage when the material is growing, when it's drawing, those plants are photosynthesizing CO2 out of the atmosphere. And then, that green line is rising as it's harvested, transported, produced, built, maintained, fixed, and then finally the building is taken down or the material is taken out and something happens to it at the end of its life. So there's kind of your trace of a -1+1 accounting for a biogenic material. And here's the path that a conventional material would take, looking at it the same way. The conventional material has no biogenic component or no significant biogenic component. So everything is an emission from harvesting, transporting, manufacturing, et cetera, all the way to end of life. It's an accumulation of emissions. what happens if we're fixated on that end of life result only is that those two materials don't look very different. You go, oh, the biogenic materials, like, yeah, you know, this percent or that percent less impactful than the conventional one, but it's not so much. And so if it costs more, or you know, if there's any other impediment to using it, it often just kind of gets written out of the design because look, it's not, you know, it's not making that big a difference. And so what we need to be thinking about in life cycle assessment is the dynamics of time and, you know, what it means to think about emissions as they occur and what happens when they occur. And in this case, when you take the carbon out of the atmosphere and put it in a building material, which lasts, you know, a reasonably long time, we can measure it in at least decades and hopefully a century or two, it's not the little green dot number out at the end that tells us what the impact that material has had on the atmosphere, on the climate. It's the area under that zero line. It's this whole green area is the positive climate impact from removing that CO2 and storing it. You know, it got removed at the start of the building process or when the material was manufactured, and it stayed out of the atmosphere the entire time that product was in the building. Alternatively, we have to think about the area above the line as being the warming impact from the emissions of a material that has net emissions. Again, it's not just this number out at the end that's sort of like a running total, it's the area. So every time this line jumps, those emissions are in the atmosphere and they stay in the atmosphere. They stay driving climate change. They make the planet warmer. It's not like they happen and go away. They happen and go away. They happen and they accumulate and they accumulate. And this initial burst of emissions is still in the atmosphere. I mean, there's some decline over a century or two, but it's staying in the atmosphere and it's driving warming. And so again, it's that area above this line that is the ongoing climate warming impact from those emissions. If you add up the area below and you add up the area above, you get a very different picture of the climate impact of those two material choices, not just by looking at the final result of a end of life stage LCA. So, you know, this I think is really important. I think there are a lot of people in the LCA world kind of realizing that the climate, you know, we don't fix the climate by fixating on a number that we're sort of, you know, coming up with to represent a material at the end of 60 years, 80 years, 100 years. That when emissions go into the atmosphere or when carbon comes out of the atmosphere, there is an immediate impact, and that impact sort of traces over time. And it's not just a, I was just going to quickly point out that also, you know, with biogenic materials, there are a way, if you look at the sort of arrows out to the side there, you know, there's always kind of a default assumption in LCA that there's sort of a worst case scenario, or I guess we call it the conventional scenario. What's going to happen to a material that comes out of a building, and we base those assumptions on what's happening with those materials today. So if today 50% of wood waste from buildings in your area ends up in the landfill and 50% is incinerated, then that's the assumption that's made for the end of life stage of an LCA. But I would suggest that, you know, whether the materials are biogenic or not, there's going to be increasing pressure over time to do more with those materials, to try to save them, to try to reuse them. Barry's presented you know, some really great evidence that that's what we need to be doing, and I think we'll see that start to happen. And so, you know, those end of life assumptions are not necessarily, you know, we're assuming that today, that 60 to 100 years out, this is what's going to happen. But I you know, think there's a reasonably good chance that we're going to be doing better with those materials, in which case, you know, if we're reusing a lot of the carbon that's in the biogenic material from that building, or we're turning it into biochar, that the carbon storage is actually going to continue, you know, for a longer period of time, possibly indefinitely. So that's another thing to think about when you're looking at LCA results. Okay, So this is not just like, oh, wouldn't this be a good idea if we thought about carbon this way? There's an entire climate science basis for doing this. It's called ton-year accounting. The notion of it was introduced in the late 1990s. And what you're looking at is sort of a graph that summarizes the notion of ton-year accounting. So in yellow in this graph is 1 ton of CO2 emissions that happen, and the sort of the gradual downward slope of that curve is showing that over 100 years, the climate impact of that emission sort of diminishes. And you can sort of say that over 100 years, the area represented by this yellow part of the graph means that 1 ton of emissions today is going to cause 46 ton years of damage, of warming to the atmosphere over 100 years. So on the flip side of this down here, 1 ton of carbon stored for, we sort of bring the line over in time until the area in blue equals the area in yellow. In this case, it's 46 years. So what that means is if we can pull a ton of carbon dioxide out of the atmosphere and keep it out of the atmosphere for about 46 years, there's definitely debate on whether that's, 42 or 53, but, somewhere in this range, then you have completely negated a ton of emissions that occurred at the same time. So if you're looking for, to say like a carbon offset market or something like that, 1 ton of carbon stored in a building, since that's what we're talking about, for 46 years is the equivalent of 1 ton of carbon emitted over 100 years. So the two things are of equal value. And so if we can keep the carbon in the building longer than 46 years, it's doing more work than just 1 ton. And I'll show you that on the next slide. But what we're trying to sort of establish here, or what we're trying to sort of point out, is that climate science understands the value of time. LCA practice has not necessarily understood the value of time, but if we were thinking about time the way that climate scientists think about time and carbon storage, then putting carbon in buildings for 50 odd years is really meaningful. It's a 100% offset of the same amount of carbon that you've stored. And so you can sort of come up with figures to scale the value of carbon storage based on this. So if you store 100 tons of carbon in a building for just 1 year, it's the equivalent of 2.17 tons of carbon offset, and et cetera. You can sort of multiply it out. So you can see highlighted here, if the 46-year time window, you store 100 tons, you've offset 100 tons. But if it goes longer, so it goes to 80 years, your 100 tons of carbon storage has actually done the work of offsetting 174 tons, et cetera. As the time increases, the time that you've kept that CO2 out of the atmosphere, the positive impact of it increases as well. So what this also means is that when the carbon comes out of a building, if it comes out post the 46-50 year window, it's essentially, if whatever gets emitted is a new emission. It's not like in the -1 +1. It's not a continuation of the old emission. It did its work. It's completely done the work of offsetting a ton of carbon, and whatever portion of it comes out, you could consider it a new emission and deal with it separately there, because it's essentially negated itself by being out of commission for those 46 years. So I hope that's a good enough framing that we can start to at least think about why biomass, why biogenic building materials have this value that perhaps hasn't been so well either understood or applied in building and in LCA practice. Now, having said all of that, forests and timber products are way more difficult to assess in this way. And the reason for that is that right now, the sort of the way we account for timber products and the sort of the emissions associated with them and the carbon that they store is it's looking through a pretty narrow window, and it may not be capturing everything that's critical to understand. So again, looking at current LCA practice, right now for timber products, the sort of the rules by which these things are done is that if your wood product is coming from a sustainably managed forest, and here, the ISO standard sort of says, FSC or SFI in North America are considered examples of that, then you can count your carbon in the sort of like -1 +1 sort of way. Now, what's weird about that is that neither the Forest Stewardship Council nor the Sustainable Forestry Initiative, nor, to the best of my knowledge, any forestry program actually tracks carbon as part of the certification. So we kind of have this, we're applying this notion that, well, they must be doing a pretty good job, so we'll just, credit them for doing a good job for something that they're not really doing on the wood side. And wood is really tricky because, oh, sorry, there's -1 and +1. There's a lot missing when you think about analyzing wood in this way. So when you do the life cycle assessment of a timber product, a bunch of things don't show up. One is that at around half of the biomass of the tree doesn't become a carbon storing timber product. So if I cut down a tree to make 2x4s, about half of the volume of that tree becomes a 2x4. The other half becomes sawdust, becomes forest slash, becomes something that gets burned by the mill to heat the kilns to dry the 2x4s. But a good half of that tree, the carbon that was in it goes back to the atmosphere almost instantly. So, we're saying, okay, great, you've got, say a ton of carbon stored in your 2x4s in your house, but a ton of carbon went into the atmosphere to get that ton of carbon into your building. So is there any climate value there? The answer is probably no, but that's not captured in current LCA. Also not captured is the volume of root mass. So, typically there's about 20-ish% of tree biomass is in the roots, and we don't use that at all in timber. And that material ends up sort of rotting and going back to the atmosphere in various ways fairly quickly. So there's another chunk that we're not accounting for. We don't account for soil carbon releases from logging, and especially from the erosion that happens after you take out a bunch of trees. So those trees have taken not only a bunch of CO2 out of the atmosphere to make the tree, but they've also put a whole bunch into the soil. And quite often when we disrupt that system by cutting down a bunch of those trees, especially by clear cutting those trees, a whole bunch of that soil carbon goes back to the atmosphere, currently not captured in a forest timber product LCA. And the final factor is that, there's this notion, well, and I think this is where the, get wood from sustainably harvested forests part comes in, is like, well, as long as we're planting as many trees as we're taking out, then the carbon balance will be kind of equal, right? Like I take out a tree, I plant a couple trees, I've removed some carbon, but I'm putting something back in that's going to store carbon. But there's a pretty big time gap, right? A tree takes a long time to grow. And so those replanted trees may not start capturing carbon at the rate that the mature tree that you took out is going to do for several decades. And, given the precarious position our climate is in, cutting down a whole bunch of trees right now and actually adding to carbon emissions in the atmosphere with the hopes that these replanted trees will take that up over the next few decades is not going to help our sort of drive to really reduce emissions right now and to do the best thing we can for the climate right now. So lots to think about in the wood space that currently isn't. The way, I guess, to best summarize it is to say, like, we're not going to do anything if we're making the pool of carbon in our global forests smaller. in the trees, in the soil, in the sort of like supporting biomass that's in a mature forest. If we're making that smaller while we're making the pool of wooden buildings, timber buildings bigger, we're not doing anything for the climate. And in fact, there's a good chance we're doing something worse for the climate. So the only way that we can say, hey, this big timber building I just made, we can attribute meaningful carbon storage to that building is if we made the building and we made the forest carbon stocks bigger at the same time. And there are people who will argue that we can't do that. There are people who will argue that we can. I don't know enough about forestry to know, who's more right. But I do know that this notion that timber buildings are going to save us because we can store tons of carbon in our buildings by using timber buildings is not necessarily going to be the case. Currently, our current forest practices do make this pool smaller while they make the building pool bigger. And so there's no climate benefit to pursuing that strategy. So you might be saying, okay, so you just told me all this stuff about the climate and meaningful carbon storage, and then you just told me, well, forests aren't, forest products aren't that. So what are you talking about? What I'm talking about is all the other kinds of biomass that are out there that we could be putting into buildings, and that some people are putting into buildings, and that I think my overall argument is that this is the stuff that we need to start getting into buildings, and this is the billions and billions of tons of biomass that is fast growing, often annually renewing, and is often biomass that's generated as sort of a waste product or a byproduct of other industries, in particular agriculture, but also to some degree forestry, and also from our waste streams. So, in some fashion or another, all of this biomass pulls CO2 out of the atmosphere, but then it goes back to the atmosphere very quickly, whether that's by burning crop stubble, or turning some trees into newspaper and then incinerating that, or turning cotton into textiles and then burying them in landfills. Whatever it happens to be, we sort of have this cycle now of generating tons of residue biomass and then letting the carbon it's captured go back to the atmosphere. And the sort of the thinking that I have about buildings, and that a sort of growing number of people have about buildings, is that buildings are an ideal way to kind of interrupt that flow. So the CO2 that we're putting in buildings, as I've sort of explained, it is or could end up back in the atmosphere. But if we're going to interrupt that cycle, if those plants are going to draw billions of tons out of the atmosphere for us, if we can put them into buildings and hold them there for, by ton year accounting 46 years, but let's be more ambitious about the lifespans of our buildings and, say, 100 years, 200 years, interrupt that. Then if the carbon goes back to the atmosphere, it's a new emission later on, and it's done the significant thing that we need to do right now of reducing the amount of CO2 in the atmosphere today and tomorrow and like over the next few decades. And so, there are all kinds of buildings with all kinds of different building materials that are using this kind of residue and waste biomass. And that's what I'm going to sort of focus on, and what I hope you kind of leave today interested in focusing on as well. So how much of this biomass is there? Lots is the answer. Here's a study in the US. This got studied really, really well in the 1990s when initial sort of thoughts about what do we do about CO2 and the climate looked at sort of biomass as replacement for thermal energy generation. So we were basically saying, oh, we got to stop burning fossil fuels, but if we burn biomass, then we'll offset all that fossil fuel use. Luckily, that thinking is kind of shifting. We're realizing that just continuing to burn stuff might not be a great thing. But what we have are all these really great calculations of how much biomass was out there. So, you know, in the US, you can see that ag residues, wastes make up a significant point, and they're also looking at how much could be generated if you actually planted crops, sort of intentional crops to create biomass. But however you slice it up, and the three different bars here, these are sort of three different estimates based on the same data. So this one is sort of like a government sponsored moderate case scenario. Here's like their best case scenario. And here's the Union of Concerned Scientists looked at that data set and said, well, maybe you're being a bit, you know, ambitious. You know, we think it's more like this. But even still, it's, you know, in the hundreds of millions of dry tons of this material available. And, you know, this kind of figure plays out around the world too, like without having to involve ourselves in massive land use change or cutting down forests. We have literally millions and billions of tons of biomass that could be available for making things like building materials where that carbon gets stored durably. So let's take, for example, a favorite material of mine, which is grain straw. There are all kinds of people making all kinds of interesting building products and buildings out of grain straw. But just to give you a sense of scale, over 2 billion tons of grain straw are grown every year to give us the sort of the wheat, the oats, the barley, the rye, the rice. You know, we eat the grains that these things grow, and they all leave a stalk that we don't eat and nobody eats, and is either burned or drowned or in some way gets back into the atmosphere very quickly. So we're already planting, we're already growing, and we're literally already collecting over 2 billion tons of grain straw. That 2 billion tons of grain straw contains 4 billion tons of carbon dioxide that was drawn out of the atmosphere to grow those plants. If we could capture that and put it in, say, buildings, that would be drawing down the equivalent of India's GHGs annually for material that's already growing and material that's already being planted, material we already have access to, and material we already know how to make materials and buildings out of. So, you know, there's people making straw SIP panels, there's people making blown insulation out of straw, there's people making compressed interior partition wall panels, insulation blocks, acoustic panels, like all kinds of things. And also people making now quite large buildings, you know, 5,000 square meter plus public buildings. You know, here are the straw bale panels being made for this school in France, for example. So, you know, this isn't sci-fi, this isn't sort of futuristic, this isn't, you know, wouldn't it be nice if, this is something that, you know, people are already doing. And if we put our minds to it, it's not a big technical leap to figure out how to do this. So I've been doing a lot of work at the residential building scale. That's kind of my focus. And in the last couple of years, have sort of run over 700 sample homes, kind of as-built homes from around North America through calculations. And to date, the sort of average is somewhere between sort of 200 and 250 kilograms of emissions per square meter of floor area for a low-rise residential building. So 241 was the average when I made this graphic. So there it is. There's a sort of typical scenario of our small buildings. At the rate that we're building those small buildings right now, that's 54 million tons of emissions a year. That's this emissions that would come from 15 coal-fired power plants, and we're adding that to the atmosphere annually while making the materials to make just our low-rise residential buildings in the US. On the flip side, if we did the kinds of swaps that we know are possible, and we know they're possible because we can see example buildings like them, I'll show you a couple in a minute, that we can get that figure to somewhere in the neighborhood of 130, 140 kilograms of net storage because of all these biogenic materials per square meter of building. If we can get from where we are now to there, we would be net storing 36 million tons of CO2 annually by making our residential buildings. So we can go from adding 15 coal plants worth of emissions to removing 10. That's the difference of 25 coal-fired power plants if we can get from this place to that place, which is a huge intervention in terms of the impact on the climate. The single biggest climate impact in my country has been when the province of Ontario shut down 4 coal-fired power plants, absolutely changed the country's GHG emissions. And that's 4 plants. And we're talking the potential for just in the US by changing it by the equivalent of 25 coal plants. So this is not like, if you look at it on a one building by one building basis, it's like, does this really make a difference? But yes, it does when we look at it at the scale that we are currently building. And here in North America, we're building a lot less than in other parts of the world. This comparison gets exaggerated if you start looking at developing countries. If you start looking at India, if you start looking at the sort of the building stats for China, of what's predicted for Africa, this gets way more intense and exaggerated. So either it gets more intense and exaggerated on the emission side, or we work hard to intervene and make it even more dramatic on the storage side. So I'm just going to quickly show you some examples of larger buildings. I know, because my own practice, my own focus is in low-rise buildings, that quite often people get the sense like, oh, that's sweet and cute, like you can do this with little buildings, but you can't necessarily do it with big buildings. So I'm just going to show you some examples. They're all from Europe, of places that are taking these notions, taking these types of materials and making large buildings out of them. So here's the school in France that I showed you a couple slides back. This one is really great. This is a major insulation retrofit of a community center, sports center in the Netherlands, using compressed straw, chopped straw, blown in to be the insulation for this really large 2,500 square meter retrofit. Here's a business park in the UK made with prefab straw bale wall panels. Here's a Marks and Spencer store in the UK made with prefab hempcrete panels and a mass timber frame. Here's a building at the University of Nottingham, also in the UK, made with prefab straw bale panels. Here's a 7-story apartment building in France, also made with a timber frame and prefab straw bale panels. Here's the Enterprise Centre in East Anglia, UK, that's using a whole bunch of biogenic materials, but really interestingly, these prefabricated thatch panels as the exterior cladding. So that's kind of taking a very old and very traditional way of both roofing and siding buildings in Northern Europe and kind of turning it into something that works for larger buildings and at kind of like a mass scale. And now this is a building that it's smaller in scale, but this is one that I can talk about a little bit more in depth because I was really involved in this building. This one is a new classroom at Trent University in the city of Peterborough, Ontario, where I'm from. And they needed a new forensic crime scene building for their forensics department. And so they were really interested in making this a net zero building. They were initially interested in making it a net zero emissions building on the operations side, which I'm obviously a huge fan of. That's what we need to be doing. And they were doing it through the ILFI's Zero Carbon Buildings Certification Program. But when they asked for our involvement, I said, well, sure, we can make a net zero emissions building, but how about we also try to make the materials net zero emissions as well. And so they were interested and joined the design team. And so we suggested a number of material substitutions to get there. One being using foam glass gravel for the insulation under the slab. So you can see in this photo here, this is made from the recycled glass that nobody knows what to do with, that we have mountains of all over the world. It sort of puffs it into a foam glass that is both structural and insulative. So it replaces the gravel you would usually put under a building's slab, but also often the foam insulation that would go there. It's not a carbon storing material, but it has a very, very small carbon footprint, especially compared to foam insulations. We made the exterior walls of the building out of this load-bearing hempcrete block system from a company called Just Biofiber. We also used hemp bat insulation on the insides of those walls and in all the sound separator walls. We used some wood fiberboard insulation on the upper portions of the building. We selected the best available low carbon concrete mix that the regional concrete suppliers could offer. And we also used a local mill that makes a charred wood siding for some of the exterior of the building. Those are the key changes. So not that many changes to the overall building plan, but you can see they already had a base case building sort of set up because they were going to build this differently. So when we calculated the footprint of the materials for their base case building, this building was going to have over 211 tons of emissions associated with making the materials. It was going to be concrete block and spray foam were the sort of like main structural materials for the walls. It was going to have a metal framed roof and either spray foam or mineral wool in the ceilings. So anyway, all of that added up was 211 tons. As built with the low carbon materials and the carbon storing materials that we applied, we got that down to 25 tons. So that's an 88% reduction. And then we also calculated what if we were calculating the carbon storage value of the timber we used in here, because we did go out of our way to try to find as much locally sourced, really sustainably harvested, locally milled wood. So again, we don't know that we're doing the right thing. So we aren't counting on these numbers, but just to show, if we're doing wood right, then we can actually get this building down into net carbon storing territory just slightly. So, but dropping the carbon footprint of these materials by almost 90% is pretty major. And so now when we say, hey, this is a zero carbon building, what we're talking about is zero carbon operationally. So it's all electric. The grid in this part of the world is pretty clean to start with, and all of its grid use is being offset by the solar panels on the roof. So, for the foreseeable future, the building's not going to contribute to climate change in its operations, and its materials, depending on how we want to calculate it, either had only a very tiny carbon footprint or they were slightly carbon storing. But either way, now we can sort of say, if we put those two things together, operational emissions and material emissions, what's the footprint of the building? And the answer for this building is it's minimal or nothing or slightly carbon storing. But this is the kind of approach that's going to actually get the built environment to be carbon neutral, at least in the sort of time frame we want. And we can't sort of just say, let's just focus on the operations. And if every small building like this is responsible for 200 plus tons of emissions while it's being made, it really doesn't matter so much how bad the operating emissions are. You've already blown your carbon budget before you've even started operating the building. So we're trying to think about these things together and make sure that when we say this is a zero carbon building, that we're actually talking about a zero carbon building. So another project I'll show you just to wrap up. We built this with our students in 2017. We called it Zero House because we were really intentionally setting out to have a zero carbon footprint building, both operationally and on the materials side, as well as including zero toxins in the materials and having the building responsible for zero waste as well. So we built one unit of what the design team had figured as a sort of stackable row house. So this was a group at Ryerson University making a proposal for the end of a city block in downtown Toronto. And so we were looking for a project to do. And so, we thought that we could sort of give them an example of how this could work, not just in a sort of, prefab and energy efficient way, which were their goals, but in bringing this sort of notion of carbon storage to the table as well. So we essentially made the building off-site. So we really wanted to not just make a prefab building, we wanted to make a prefab building that you could put together and take apart and put together and take apart. And in doing so, earlier on I was saying, if we can extend the lifespan of this carbon in buildings beyond the lifespan of one building, then we extend the carbon, the value of storing that carbon. And so we were seeing a lot of people doing interesting things with prefab, but nobody was planning on making their prefab buildings to take down again. And we really wanted to go about it that way. So to challenge ourselves, we decided to make the panels, assemble the building in our hometown of Peterborough, let people see it, take it down, put it up at a design show in Toronto, Ontario, let people see it, take it down, and then sell it to a client and put it up on their property. So in our little flying factory, we built floor panels, wall panels, and roof panels, mostly with wood framing and using different types of carbon storing insulation. So a lot of the wall panels had straw bales in them. Others had cellulose insulation. They all had re-wall, which is a recycled drinking box, juice box, wall board, and wood fiber board sheathing, which is like a structural exterior insulated sheathing. So the panels were kind of loaded with waste biomass carbon storage. We did a few experimental things like sheathed some of the panels with mycofoam, which is a mycelium-based insulation that we grew kind of in situ on several of the panels, just to give that a try. Worked really well. That's a material I'm really excited about in terms of being able to make building materials that get us completely outside of the notion of like you go out into nature and you like harvest things and then you shape them and turn them into products, and instead looking at how can we actually grow the materials that we need. It was really exciting to pull the cover off of these panels 4 or 5 days after we inoculated them and see that we had this incredible fireproof, highly thermally resistant, moisture resistant insulation that sort of grew all on its own. So we put the panels up. They're going up for the second time. It's really quick. We can assemble the entire structure, floor, walls, and roof in a day. We also wanted to make sure that we were thinking not only just about the structure as being removable and going up and going down, but also the interior and exterior finishes. So on the interior, we used a lot of pre-finished plywood with really attractive surface mounted screws so that everything could go up, but everything can also come down at any point in the future history of this building. If somebody wants to rewire or make alterations, it's easy to pull off whichever pieces of plywood you need to get back into the service cavity. We did some demountable plaster walls as well. On the right, you can see a sort of shiny red Cadillac plaster. So that was in the hallways and in the bathroom. So the floors, the flooring traveled with the panels, and you can sort of see that there's a piece of hardwood flooring running the opposite way. That's the seams, and that's how we handled that. So in all facets of the building, really trying to figure out how to make sure that all the materials are reusable and can be taken down and put back up again. You can see on the exterior that meant we used steel cladding, which from a carbon footprint point of view, was definitely a penalty to the overall carbon footprint, but it made a whole lot of sense in terms of being able to mount and dismount an exterior finish repeatedly. So when we tallied up the carbon footprint of this house, our net carbon storage was 25 tons. So that's, even taking the metal siding and the metal roofing and all of those things into account. The carbon storage in the biogenic materials offset all of those to the tune of 25 tons. And a house of this size built conventionally would have added about 45 tons of emissions through the contribution of its materials. So, this was a really great project to kind of show not only that this can be done, making carbon storing buildings, but that it can be done in a sort of like efficient and prefabricated way, and in a way that doesn't generate a lot of waste at the end of the building's life too. And just as a side note, it's not necessarily related to the carbon footprint as we calculated it, but those 3 bags of garbage is all that was generated in the production of that house. Every other material was recyclable. So we were very proud to send only about 20 pounds of waste to the landfill, rather than the typical 8,000 pounds from a Canadian new home. So I'm going to wrap up by basically, inviting you to be bold and be radical in your approach to the built environment and its carbon footprint. I hope that I've showed you enough examples of buildings at all kinds of scales that people who are dedicated to the notion of building this way, of doing these kinds of calculations, of taking the notion of biomass buildings seriously, they're making serious buildings and they're doing it really well, and it's potentially transformative for the entire practice of architecture and for the global climate. I'm sure somewhere along the line you've seen the impact that buildings have globally on our climate, and what I would like us to think about is not just like chipping away at that by incrementally reducing. I want to see us flip that paradigm completely. And, I would like to invite you to be part of doing that. You can make these kinds of buildings. You can advocate for them, work on them, design them, help get them funded, whatever piece of this is yours to take on, that you take the climate crisis seriously and really, give it your all to do this thing where we can flip this around and become like actually the building industry a source of really massive carbon storage instead of one of the main driving factors of climate change. So a sort of off the cuff action plan, having seen this and hopefully you being excited about this now. Build with plants that ideally also build soil. So we didn't really talk much about that, but if the biomass that we're using in buildings is grown in such a way that we're also retaining the carbon that those plants put into the soil instead of just tilling it up and releasing it, we're kind of going to get a double bonus. And I didn't talk about that because it's a difficult one to account for, but it's meaningful, and it potentially doubles or triples the impact of a biomass building if the carbon that plant you built with stays in the soil. There can be as much or more carbon in the soil than there is in the biomass that you built with. Fix what we have. I know that Larry has talked to you about that. If we can not expend so much embodied carbon on making new buildings, the ones that are there, the carbon's already in the atmosphere. And I would add to that by saying, fix what we have, again, using these biogenic materials. If we can be insulating buildings, wrapping buildings, cladding buildings, flooring buildings, putting dividing walls in buildings, if we can do all of that with biomass, those retrofits also have the potential to be massive storers of carbon too. Think about where your materials are coming from and how you get them. There's a danger, from a quick presentation like this and just thinking like, all biomass is great. Let's just, take every bit of biomass and jam it into a building. There are ways to do that well, and there are ways to do that that will just continue a cycle of poor land management and bad farming practices and all kinds of wasteful and destructive behaviors. So please think about a deep dive into where these materials are coming from and how they arrive at your building site. There's a lot that we can do right now with current technology. The buildings that we can make, I showed you a bunch of them. Really simple materials like cellulose insulation and wood fiberboard insulation and linoleum flooring. There's a whole bunch of things out there right now that we've used for decades that have good track records, that are affordable, that are available, and that store carbon. So like, use those and be encouraging of exploring, co-partnering with the people who are making better stuff. We really need to change the codes and get everybody educated. I'm really heartened by the amount of codes work that's starting to happen on the embodied carbon front. Here in Canada, our Prime Minister just charged Natural Resources Canada, which is the department responsible for energy efficiency in buildings, with making a new building code that aligns with the country's climate targets by 2024. That, couldn't have imagined that change coming around that quickly even a couple of years ago. And I see similar pushes happening with the International Code Council in the US. So anything that we can do to support those efforts, whether it's just writing to those bodies and saying, yay, like, good for you, keep going, this is what we want, to actually joining them and helping out. Learning how to count carbon and what the numbers mean. This presentation gave you the quick 15-minute intro into how to think about biomass and carbon storage in buildings, but there are all kinds of tools and accounting softwares out there, lots of which don't think about carbon storage or think about it in some of the limited ways that I pointed out. So if you are starting to learn LCA tools, question those tools, question the people that made those tools, question the results you're seeing, and think about them in terms of the time value of that carbon, and be sure that as you're coming up with results, you're coming up with results that you feel represent the way that the climate is being impacted. Build relationships of mutual aid with people beyond profit. There's a lot of people who make a living making these types of buildings and making these materials, but we're also doing it because we have to and we want to, and because we find that the relationships that we establish as we find mentors, as we find colleagues, as we find clients, that all of those both help us get to our climate storing goals with buildings, but also reward us and make this all possible to do personally. Build understanding of and relationships with ecological cycles. That's in some ways a repeat of number 1 and number 3 here, but we need to get beyond the notion of building materials as something that we like look at a website or look at an order sheet and say that one, to really having a clear sense of who's involved, what are they doing, how does it happen, how are they treating people, how are they treating the planet, what are the climate impacts beyond the numbers that I see on an environmental product declaration. I think that's all really important. And last but definitely not least, there is incredible urgency to do this. It's exciting to see the handful of buildings I just showed you that are great carbon storing buildings, and we need to get every building looking like that in the next 10 to 20 years. And so it's urgent that we do this. We're beyond the point of like, you have 1 or 2 of these projects on the back burner, stewing away while you're kind of doing your other work. We need to make doing it this way everything we do quickly, and to want to do it and to love doing it and to really embrace doing it. I think personally, I can't tell you how much energy and joy, as well as some good moments of despair, but come from really diving into this and really making this the focus of what I do. And I hope there's some encouragement between what you've heard from Anne and Larry and now myself to do this yourself. So I want to thank you for inviting me to talk, and I'm looking forward to chatting with you live when the Q&A comes up. Okay, bye.
All right. So you've heard about how to reduce embodied carbon using lower carbon materials, and how to eliminate it and store carbon using carbon sequestering materials. Chris and the Carbon Leadership Forum and a lot of others are really working on these kinds of reinventing, rethinking materials and how we build, which is really exciting and really has to happen. As Chris said, we have about 10 years to completely change the way we think about and use materials. There's another way to eliminate embodied carbon, and that is to use fewer materials in the first place. The easiest way to use fewer materials is to reuse the buildings and materials we already have. The built environment is not just a potential carbon sink, it's a huge carbon bank. Reusing buildings, including renovating and upgrading them, results in about 50 to 75% less embodied emissions than building a new one, and makes it possible to build fewer new ones. The other huge benefit from reusing buildings is that if you make them more efficient and all electric, you can reduce and eliminate operating emissions from all our existing buildings, which account for the majority of emissions from buildings. Here's how emissions break down for new and existing buildings. And I'm going to preface this by saying that this is for the US, and we build a lot less in the US than we build in a lot of the rest of the world that's rapidly developing. So this embodied bar in the center would go up a lot for the global picture. In the US, we built about 4 billion square feet, 2/3 residential and 1/3 commercial, in 2018. The emissions from operating that 4 billion square feet is somewhere between 10 and 20 million tons a year, depending on how efficient they are. The emissions to build that is about 150 million metric tons. But the emissions from operating the 340 billion square feet of buildings we already have is just under 2 billion tons. So for new buildings, as Chris has said, we really need to focus on eliminating embodied emissions. For existing buildings, we need to work on eliminating operating emissions. Reusing and upgrading buildings addresses both of these. Reusing buildings makes it possible to build fewer new ones, which brings down embodied emissions. Upgrading them brings down the operating emissions. And if we can use biogenic carbon storing materials in our renovations, we can turn existing buildings into carbon sinks as well. I'm going to show you a little case study that we did a carbon study after it was done. We did a study of this building. We weren't the architects for this building. It's a net positive office renovation for DPR construction in San Francisco, and it illustrates how important operational savings are and embodied. The project resulted in about 70% less embodied emissions than a new building would have produced. Reused materials were shown hatched here include the structure, the slab on grade, cast concrete exterior walls, and the historic aluminum curtain wall, windows, and mullions. So the solid bars are the new materials that went into the building. The hatched bars are what we saved. And it's about a 70% reduction, which is pretty significant. But here's the deal. The embodied carbon compared to a new building was about 650 tons of savings, which was significant because it happened up front when the project was first done. But over the next 20 years, eliminating gas, adding efficiency upgrades and PVs will yield far greater savings than avoided operating emissions. So you got to do it all. You got to do the embodied emissions, which saves emissions right up front, which is where we really need to save it. But then you have to keep the operating emissions down and get them to zero. And this actually is a net positive building. It produces more energy than they use. So it goes back to the grid. But it's not easy to convince people to reuse buildings. Developers and architects like shiny new things, and we still need new buildings. There are also a whole lot of variables to consider. What if you can only improve the performance of an existing building by 50%, but you can replace it with a net zero building. How do climate zone, grid efficiency, and time affect those calculations? We haven't had a simple tool that could compare all of those variables. I've been working with Aaron McDade of Architecture 2030 and Laurie Ferris of Goody Clancy Architects in Boston to develop a tool that compares all of the carbon emissions, operating, embodied, and avoided, for different existing, new, and reuse scenarios. This is not a design tool. It's a tool for planners, building owners, and developers to understand the carbon impacts of their decisions and to evaluate whether to renovate or upgrade or build a new building. Here's how it works. You enter data about the existing building, including location, which automatically establishes your climate zone and grid efficiency. You define the type of replacement building you need and the type of upgrade it needs. You define the extent of the building retrofit. You set efficiency targets for the new and retrofit scenarios, and it gives you the embodied operating emissions for each option. You can see emissions over a specific time frame selected. In this case, I think it was 10 years. And you can see that the existing do-nothing building, just leave it alone, let it keep operating, retrofit that existing building to a certain efficiency standard, or the new building. And you can see that in this case, for this particular, was one of our projects we did right near the Berkeley campus, it was far less to retrofit and upgrade, mostly an embodied savings for that. It was developed in Excel. We're currently converting it into an open access web-based app. We're also working on versions that will allow cities and developers to evaluate whole portfolios of buildings, because this isn't just about single buildings, it's about reusing and upgrading thousands and millions of buildings. There are a number of tools out there that can help you understand, track, and reduce embodied carbon. Databases give you carbon emissions per kilogram of material, so those are useful just to sort of take a quick look at different materials. Carbon calculators track total embodied carbon emissions for buildings and building assemblies based on material quantities. And there are a few more in the works, including the CARE tool that I just showed you, an EPIC tool, which is by EHDD Architects, which is coming out soon, and Chris's tool, which is the BEAM calculator, which is the only one that currently tracks and calculates carbon storing materials. We're hoping to add those kinds of options into the CARE and EPIC tools as well, but they're not there yet. So I'm going to go through my action plan, and if Chris isn't here, we can go back to that if we want, or we can just talk through it. So as you might expect, the top of my list is to care for and improve what we have, to reuse and upgrade existing buildings. But second on my list is what Chris is doing, which is to shift our material economy to carbon storing materials. More immediately, we need to use less concrete and build with low carbon concrete. We use more concrete than any other material in the world, and it counts for over 8% of global emissions is just from concrete. So concrete, a lot of people are working on concrete. We really need to keep working on it and get rid of it and make it better. Choose the lowest carbon alternatives for all materials, which includes recycled content materials and salvaged materials. We need to maximize structural and material efficiency. We need to just use fewer materials in general. And finally, for me, reuse is also about, it's about caring. That's why we named the tool that. Caring for the people and communities who live and work. Most people live in existing buildings, not the new buildings we're building today. So we really need to start treating our existing built environment, not just as carbon sinks and ways to save carbon, but as ways to make communities better and serve people better. So let's see, I don't know if Chris is on. Do you know if he's joined us, Ann?
I don't know. Ian?
Not at the moment, not yet. We're
Chris?
still
Okay.
I mean, we can either just show this or we can go back to that and hear him talk about all this, because he's got something to say about all these points. What do you want to do? We have time to go back, or should we just?
Why don't we go ahead and take some questions for you, Larry, while we're
Okay.
giving Chris a few minutes to sort of wrangle through the technologies.
Okay. All right, I can leave this up, and then when Chris joins us, he can just talk to his action plan, his points, which have some of the same things. He's got some bigger picture things like changing the codes and all those things, which are clearly really important. So
All right.
All right.
So, Ian, do we take a show of hands, or how are we managing the questions?
We can go through some of the ones in the chat that maybe haven't been addressed yet, and then we can go by show of hands.
Okay, I kind of think we got, let's see what, here's one. Okay, Michael, what's the current cost difference of building a carbon negative typical residential building? Are there projections, I assume you mean as opposed to a conventional building? And are there projections on what this cost differential would be if materials are mass produced at high scale and practices were widespread?
Yeah, Chris really should answer this question, but I can say that Chris is building his smaller scale buildings now at really no cost difference at all. The only caveat I would say to some of the materials that he talks about is that they're not as readily available yet as you can't go to Home Depot and buy all those straw panels. So they take a little more searching for. So I would say the extra cost and onus is right now on the architects and the specifiers to find the materials. But in terms of actually purchasing them and working with them, it doesn't really cost any more right now. Chris has done a lot of these buildings, and it should be eventually, I would think, cheaper than relying on a scarce resource that's disappearing, which is oil.
Yeah, I'd like to take this opportunity to make a point I like to make as frequently as I can, which is that whenever we talk about whether there's a cost premium something, we have to go back to the assumptions of a project, right? What were the goals of the project? And if the goals of a project are to create something that's extremely low in carbon or carbon positive, then it's a question not of is it going to cost extra, but how are you going to meet your budget and do that, right? We make many design choices in creating a building, and if your goals are to achieve a particular performance objective, then you need to figure out how to do that within budget. And what's really gratifying to me is I've been harping on this for many years, and I guess starting maybe about 5 or 6 years ago, several large architectural firms and engineering firms actually did studies where they demonstrated that that was the case, that there really isn't a premium, for example, to a LEED Platinum building when that's the case, or a living building challenge, because you have to meet the goal. My favorite, very simple example is if somebody comes to you and says, well, we want to remodel our kitchen. You say, well, would you like a sink with that? Well, yeah, of course. It's a kitchen. It needs a sink, right? It's not optional. So it's a question of what you deem to be optional and what you deem to be necessary in a project. Right. And I think we're beyond the point where we need to see saving carbon as necessary. End of homily for the moment. Let's see, there's a question. Yeah, sure. Like I said, never miss the opportunity to get on that particular soapbox.
Yeah.
Let's see, Robin, is there a way to put these ideas into a general plan update? Oh, gosh, that's another favorite question of mine.
Go for it.
Thanks. Yeah, I live in Petaluma, where we're in the midst of a general plan update, as a matter of fact, and I'm talking to some of my colleagues up here, including one who's on the line today, about how we might do that. And so I've been kicking around this idea for a while of creating a carbon budget for a city that's based on sort of what is the livable planet allocation of our carbon emissions? How would we distribute that over the next 8 years in order to achieve the town's carbon neutrality goal of or by 2030, and then decide, well, how are we going to allocate that to the buildings that need to be built and renovated, which is a bit of a high bar, but again, it's like we have to decide what's necessary. So, and then to build that mechanism into our general plan update. So this is by no means a done deal, but this is the wild hair we're working on up here in Petaluma, and I would certainly encourage you to get in touch with me if you want to help with this project. So I will put my email into the chat.
And the only thing I would add to that is for general plans, if cities could start to include embodied carbon in their calculations, which aren't currently in their calculations at all, and include what Berkeley's working on. They were the first city to ban gas for new construction. They're now working on trying to retrofit the entire city off of gas, which is a huge undertaking, but it's where we have to go. So starting to have your city start to look at both the embodied end by saying these are actually emissions, even though those embodied emissions may not have been produced in our county because the materials came from somewhere else. We have to count them because we're using the materials. And then at the same time, sort of saying, going to net zero emissions on all our buildings, and existing buildings is the tricky thing for general plans, because they generally address a lot of new construction, new codes. We have to figure out a way to start to get all of our existing buildings to zero on that same timeline, or maybe a few years after, but not much after, because that's where most of the emissions are coming from, is existing buildings, not new buildings.
Absolutely. And Andy's pointed out in the chat that San Luis Obispo Public Works is exploring low carbon concrete standards for new infrastructure projects. Right on. Yeah, infrastructure is a huge consumer of, or producer of CO2 emissions. And
Chris is waiting to get in. There he is. Okay, good.
Oh, great. Chris, you're with us now?
Maybe.
Chris? Hello?
We'll see.
Yeah. I'm just wondering if he's in but muted. Maybe not. Okay. Anyway, so perhaps we can have one more question while we wait for Chris to be with us in voice.
Mm-hmm.
So let's see, what else do we have up here in the chat?
It looks like Chris has connected to audio. Are you with us, Chris?
Oh, there we go. Am I coming through?
Yes.
Yes. Hooray.
Great.
All right. So
Okay.
Chris, your action plan is on the slide next to Larry's side by side. Larry, do you want to walk him through that?
Yeah, we moved your action plan out of your slides and put it as the last slide. So if you are willing, I talked through my action plan, and if you would be willing to talk through your action plan, and then we'll take some more questions, because I thought it was a great close to your presentation. We wanted to close the whole presentation.
Sure. Okay. Hang on. Let me just get it large enough that I can read it. There we go.
Uh-oh. I can read them to you, too.
Okay. So, yeah, I mean, it's very much based on the notion of how we work with biomass. And so, point number one is build with plants that build soil. And I led with that because I didn't really address that in the presentation part, but there's a whole other part to building with biomass where if we grow the plants well, as much carbon will end up in the soil as ends up in the plant matter. And our sort of LCA methodologies don't really have a great way of accounting for that, but I think it's sort of an important thing to think about as we think about biomass and sourcing biomass and using biomass, that we're aware that there's this whole other component where we can either grow biomass in a way that sort of takes carbon out of the soil and puts it back into the atmosphere with lots of tilling and sort of conventional practices, or we can harvest biomass where we're intentionally getting carbon back into the soil at the same time. Point two is to fix what we have, which I think is what you covered probably very well, Larry, to think about not building new unless we have to, focusing on where materials come from and how we get them. Related, I guess, to the first point about building plants that build soil, but more broadly, thinking about labor practices and supply chains and all of those things that go into getting materials to buildings, and doing our best to make sure that the whole sort of ecosystem of getting materials is healthy and good for everybody. Doing what we can with current technology, because there are lots of things that we can do that are either low carbon or carbon storing today. And then, as I sort of showed in the presentation part, lots of new things coming, things that are available, but in small quantities, or you'd have to actually, track it down, and things that are still in R&D, but always keeping our eye towards, what else is coming. Changing codes and educating everybody quickly. I guess that's what we're all here for today. It is really great to see what's going on with codes and climate much faster than I thought would happen. Here in Canada, our Prime Minister just gave a directive to Natural Resources Canada, which is sort of the buildings energy efficiency branch of the government, that we need an entire new building code based on our climate commitments by 2024. And that's something I would never have imagined coming along as quickly as it did. But and it seems like there's interesting things happening at the ICC level in the US. So that's great. Learning how to count carbon and what the numbers mean is my next part of the action plan, which is sort of what I was trying to cover a little bit in the presentation. Build relationships of mutual aid with people beyond profit. This is, I put that there because we can all make a living doing this really great building and design work for the climate, but that, if that's all we're doing it for, and we're not pursuing relationships and support of everybody involved, we're going to kind of replicate a lot of the same problems that we've already created. Build understanding of and relationships with ecological cycles. I guess encompasses a lot of some of the first points. So I'll jump to the last one, which is act with great urgency, tremendous passion, and abundant joy. And that's because there's a lot that we need to do. It needs to be done quickly, and we need to feel sort of joy and exuberance and excitement at being able to tackle this pretty huge issue.
Thanks, Chris. I that last point is so important, because for me, even with the work that I do, you get overwhelmed by reading the news and reading what's happening. And the way to not get overwhelmed is to act, is to do stuff. It keeps me sane, actually, by continuing to find ways and strategies to reverse what's happening. And I think we still can. And I think that's how you don't go. I have a lot of people that just get totally depressed when I try to talk about climate with them. And the way to not get depressed is to do stuff.
Yeah.
Yeah, I totally agree with that too. And in fact, I have a no news policy. Somehow the news finds its way to me anyway, but it's like, I don't want to read it. I don't want to hear it. Just like keep me focused on solutions.
Right.
So Chris, thank you so much. I'm so glad you're able to drop in for this Q&A part of the session. And so folks, should we do hands raised? Because I think we have run through all the questions in the chat. We can actually unmute people to have them express their questions viva voce, right?
And should I stop sharing and then we can just go to see everybody? Is that
Sure.
okay?
Yeah.
Sure.
All right, good.
I think there is the one from Michael that we didn't get addressed, that we deferred to Chris on.
Did we?
We tried to answer it without Chris.
Oh, right. Sure, we can go back to that. And then Andy has one too. So Chris, Michael asked, what's the current cost difference building a carbon negative typical residential building versus conventional? And are there projections on what the cost differential would be if the materials are mass produced at scale and the practices were widespread?
Well, the answer to the first one is relatively simple in that, there are quite a few practitioners here in Canada, and I'm sure in the US, who are already doing buildings, residential buildings at sort of, carbon neutral or carbon storing at market rates right now. So there's not necessarily any cost difference. What I found, I did a study for Natural Resources Canada, and we found no correlation between the carbon footprint of a material and its cost. So sometimes the material with the best carbon profile was the cheapest, sometimes it was the most expensive, sometimes it was mid-range, and vice versa. Sometimes the one with the highest carbon footprint was also the most expensive, or it could be the cheapest. Like, it's not really an indicator. It's not one of those things where, oh, because it's low carbon or carbon storing, it's therefore more expensive. It's kind of all over the map. And to the second part, I can only assume, the way that it's happened with, pretty much everything in our supply chain. Solar comes to mind. Solar was always going to be way too expensive. Nobody was going to be able to afford solar until suddenly we needed enough of it that it's now the cheapest form of energy production available. So, I think if we're serious about producing materials that store carbon, we can, we will find that they're very affordable. At heart, it's taking, leftover material that's already being harvested and treating it pretty minimally. Like, in general, there's not a lot of chemical transformation. There's not a lot of heat-based transformation. So, they should be the types of materials that we can produce, in quantity really affordably.
Great. Andy, you're up.
Great. Thank you so much. This has been a fabulous presentation. I really appreciate the examples. And I feel like a lot of the reluctance on trying some of these materials are, what if there's a fail, right? So it's one thing in kind of an educational project, but if we, client is paying us for their great building and we're trying some new product that maybe we're not familiar with. So I'm just wondering if, one, you have any stories to share, because it's always good for those lessons learned, but also if you have kind of a heads up or a process that you use to kind of discern materials that you're going to be bringing on, whether it's a hempcrete or a fiberboard or, something that's maybe not as familiar.
Well, I think in my own practice, the thing that we've sort of realized and often don't touch on it in the presentations is that there's also a real building science benefit to working with biological materials if you're aware that that's what you're doing and you do it well. All of our wall systems, for example, are sort of vapor open wall systems. So we're making airtight buildings, but we're not using any plastic sheet barriers or anything like that. And the interesting part about that is the resilience of the building and the danger of issues seems to go way down. After 25 years in the business, I have yet to see, a straw-based building or a hemp-based building or a cellulose-based building that has any of the issues that people are worried about them having, unless somebody's done something, not smart from a building science point of view, like put a vapor barrier in the wrong place, or I guess that's pretty much the only real issue that ever crops up. And so if you sort of have your building science wits about you, the fact that these materials are able to sort of absorb moisture and release it again to either side of an assembly makes them really resilient to all kinds of conditions. When conditions change from hot to cold, or from dry to humid, they actually perform incredibly well.
Yeah, the only thing I would add to that, I agree with that completely, is just the only thing to think about. A lot of modern materials like foams and things like that are kind of impervious to water, and bio-based materials are not. So it's not just the breathability, and the moisture is something they do very well. They don't do well with actually direct water. So you just have to be really careful in detailing the building to shed the water away from the material itself. And then they're great, and probably better than all the materials we're using now.
That makes a lot of sense. Thank you.
Great. Do we have other questions? Seeing any other hands? If not, I have some questions for Chris. Chris, on one of your slides where you're showing sort of an array of bio-based materials beside this, I believe it's a French school, one of your captions reads 2.16 billion tons of grain straw annually equals 4 billion tons of CO2 drawdown. And I'm curious about how that sort of 2x math comes about. How do you get twice as much CO2 as there is in the mass of the straw?
Well, that's you get that by photosynthesis. So it draws 4 billion tons of CO2 out of the atmosphere, and then the plant lets the oxygen go and retains the carbon. So when it's drawing CO2 out of the atmosphere, it has the sort of atomic weight of 1 carbon and 2 oxygens. And then when the plant does its photosynthetic magic, the oxygen goes back to the atmosphere. Thank you, plants, for giving us something to breathe. And the carbon stays in the material. So like quite often in LCAs, like you keep working in CO2. So because when the carbon comes out of that plant material, whether by burning or decomposition, most of it is going to recombine with oxygen. So it's going to turn back into CO2. So if it's drawing 4 billion tons down, if you burnt all of that straw, you'd be putting essentially 4 billion tons of CO2 back into the atmosphere. So what you're seeing is sort of the difference between the weight of the material, which is the carbon and the other things that make up the plant stem, versus CO2 as the greenhouse gas that we're discussing.
Got it. Thank you. That's really helpful. And is that roughly the same equation for other biogenic materials, or do they vary considerably?
Nope. Pretty much all dry biomass is somewhere between like the high 30s to the low 50% carbon content. So they do vary by 10-15%, but sort of roughly speaking, most people use, if it's wood, they use 50%, and if it's straw and other sort of ag biomass, it's like 40 to 45% of the weight of the biomass is carbon from the atmosphere.
Okay, great. That's really helpful. We also had a question earlier from Judy asking about the equivalency per the ISO standard of FSC versus SFI. And for those unfamiliar with the acronyms, FSC is Forest Stewardship Council, SFI is Sustainable Forestry Initiative. And there has been a long raging debate about the equivalency or non-equivalency of those two standards. So my latest intelligence is not all that recent, but at the time I last looked at it, FSC was still held by forest advocates to be considerably superior sort of across the board in terms of environmental and sustainability parameters to SFI. Do you have recent intel on this issue?
Yes and no. SFI has also, I don't know if they've put their new standard out yet, but I know they have been working quite hard on a sort of update to their standard to make it more rigorous. And interestingly, one of the things that they're intending to add is a way of sort of assessing the carbon impact of the forestry practices, which is something that FSC currently does not do. So, I think, I don't think, from what I understand of the whole issue, which is incredibly complex, is that, neither of those standards assures that there's any net balance of carbon staying in the forest ecosystem because of their practices. At best, that ISO standard is kind of just assuming that, well, if you do good forestry, you're not upsetting the carbon balance. But I think there's lots of evidence to say, well, we very well might be and quite likely are. And until we're actually measuring that, it doesn't seem like the right thing to do to just assume that the carbon we're taking out of forests is being replaced at a reasonable rate. So, I think the way the ISO standard sort of handles wood by using those two forestry, certifications is not really adequate. I think it's sort of an unfortunate shorthand that we don't know whether it's doing the thing that they're assuming it is doing.
And I was looking into this just last year, and I think that the factors that seem to affect carbon in a forest the greatest by different forestry practices are, one is the rotation length, how long you're letting a tree stand before you cut it down. And if you can let it stand longer, you're going to sequester more carbon in the forest than if you rotate it every 20 years or 30 years. So longer rotation times really matter. The amount of, one of the differences in years past between FSC and SFI was the amount of buffer zone they had around streams and things like that. And having a larger buffer zone seemed to make a big difference. Smaller clear-cut areas, SFI used to allow larger clear cuts in acreage than FSC did. All those things, when you do a clear cut, you really start to impact the soil carbon. The carbon comes out of the soil when the tree canopy goes away, and so it comes right out of the soil when it's exposed. So all of those things, I think, are ways you can get at how to increase the carbon storage of a forest, but nobody, as Chris is saying, is actually really measuring it yet. And they're trying to. There's people working on it, and I think probably it'll be out. In a few years, people will be taking forest carbon into account, which is really the bottom line, not the other carbon, the whole forest.
Yeah, no, and I think, to be fair, that essentially the differences in practice between SFI and FSC, in many cases, the FSC practices that have been more rigorous have been implicitly, if not explicitly, around some of these issues, around more effective treatment of the resource as a whole, including carbon performance.
Right, and they're getting closer and closer together all the time. I think
Right.
that's true. Yeah.
Yeah, FSC has been a forcing function for SFI for sure.
Mm-hmm.
So, okay, other hands, other questions or comments for our esteemed speakers? Okay, well, there's nothing wrong with ending a few minutes early.
Oh, there's one.
Yeah.
Oh, we got one?
I have a,
Oh, yes.
well, go ahead.
Okay, Ned, go ahead.
Oh, yeah, I just wanted to just share appreciation for the ecological insights I've heard throughout the presentation. It's really, from the architecture community, I really appreciate that. So thank you very much.
Great. Ian, you had a question or comment?
Yeah, I have a few closing remarks that we can give, and then we can wrap things up a few minutes early, if that works. Larry, I have one or two slides for closing on your.
I'm going to go back to that right now. Hang on a second.
Okay.
I realized a share screen, and then I'm going to make it full screen in a second.
Awesome. Perfect. Yeah, I can verbally do it also. But yeah, Larry, Chris, thank you for joining for Q&A, especially. That was awesome to get some context behind some of your slides and points, and you as well. Thanks for chiming in. And everybody who joined today, really to contribute to the conversation. That was pretty awesome to see the wealth of knowledge in our communal group. We'll be making slides and the recording viewable for you all that registered. I'll be sending those out probably Friday, Monday at the latest, for you all to review and take in anything you may have missed. I recognize that the audio for the video could have been a bit better, so we'll try to to accommodate that when I send things out. Also today we had AIA Health, Safety and Welfare units available, 2 of them. So in registration, any architects could have and should have included their AIA number. If you did not when registering, feel free to reach out and we can get that all shored up. We have a lot of upcoming courses, especially through March is pretty packed. We're continuing with our Energy Code Connect code cycle preview for the 2022 Energy Code. So we have a single family projects, multifamily projects, and non-residential projects courses coming up throughout the month of March. We also have an all-electric building stories from the field presented by Inbalance Green Consulting on March 10th. And then at the end of the month, we have a BPI certificate for contractors on healthy housing principles, as well as our regional forum focused on household education. What is the big deal about heat pumps and electrification on March 30th? You can visit our website, which I'll link to in the chat here for more event specifics and registration. Otherwise, on the next slide is just some contact information, our website as well. You're welcome to reach out anytime at info@3cren.org. We love to hear from you all and kind of gauge you all on what you're looking for us to host and really any other industry insight you may offer. With that, I will thank you all again and we can close things up. All right.
Thanks, everyone.
Thank
Thanks all.
you.
Enjoy the rest of your day.
Yeah, thanks.